The next topic is PVST Plus or Per-VLAN Spanning Tree Plus. PVST Plus is a Cisco proprietary protocol that extends the standard spanning tree protocol by creating a separate spanning tree instance for each VLAN on a network. This allows for a more efficient use of network resources and better load balancing, as different VLANs can have different root bridges and forwarding paths. In PVST, it runs a separate spanning tree instance for each VLAN. With PVST, each VLAN has its own spanning tree instance and topology. This makes better use of network resources and improves overall network efficiency. PVST defines different loop-free topologies per VLAN so that different traffic takes different paths over the switch networks. Let's now discuss PortFast. PortFast enables a port to skip listening and learning states and go straight to forwarding, allowing the port to forward traffic immediately upon link-up. This speeds up network connectivity for end devices as they don't have to wait for STP to converge. It's particularly useful for devices like PCs and servers that need to connect quickly. PortFast is configured per port. When the port becomes up, STP puts it into a forwarding state right away, skipping the listening and learning states. It should not be enabled on ports connected to other switches. This can create loops. But what if someone connects a switch to a PortFast interface? PortFast only works on access ports. If an interface becomes an 802.1q trunk, the feature is automatically disabled. Let's now configure PortFast. The PortFast feature is disabled by default on all switch ports. There are two methods you can use to configure it on one or many ports. You can enable it globally or per interface. This is how we configure PortFast on the interface only. First is enter the interface configuration and use the command spanning tree PortFast. We can verify that the interface is configured with PortFast using the following show command. In the output, we can see that the port is in PortFast mode. You can set PortFast as the default for all switch ports with one global command, spanning tree PortFast default. This will automatically enable the feature on all ports that are in access mode and will disable the feature on the ones that are 802.1q trunks. We can verify if the command is configured on the switch using the show spanning tree summary command. We can see in the output that PortFast default is enabled. For exam tips, PortFast is used for access ports, not for trunk or uplink ports. PVST Plus supports 802.1q and uses spanning tree compatibility for non-Cisco switches. Next topic is Uplink Fast. STP Uplink Fast is a Cisco proprietary feature designed to accelerate spanning tree protocol convergence after a direct link failure on a switch's uplink to the root bridge. It allows a non-designated port to immediately transition to the forwarding state, bypassing the listening and learning states when the root port fails. This significantly reduces downtime compared to the standard STP behavior, which would require a 30-second delay. The Uplink Fast feature is designed for access layer switches, those at the edges of the spanning tree. It allows these switches to quickly switch to a backup link if the main root port uplink goes down. How does Uplink Fast work? First, it detects the root port failure. Uplink Fast monitors the root port. When it detects a failure, it identifies the next best non-designated port as a potential new root port. Next is immediate forwarding. Instead of waiting through the listening and learning states, the selected alternate port transitions directly into the forwarding state. Next is bridge priority and port cost. Uplink Fast modifies the switch's bridge priority, typically to 49152, making it less likely to become the root bridge, and increases the port cost of all its ports, further ensuring it doesn't become the root bridge unnecessarily. And last is the MAC address table updates. Since the switch's MAC address table may be outdated after the root port failure, Uplink Fast may also flood the network with dummy multicast frames to update the upstream switch's MAC address tables via the new root port. Let's now configure Uplink Fast. We can enable Uplink Fast globally by going into the global configuration mode and use the command spanning tree uplink fast. Once enabled, Uplink Fast works across the entire switch and all VLANs. This is different from PortFast, which works on per interface basis. To verify if Uplink Fast was enabled, we can use the show spanning tree uplink fast command. And we can see in the output that Uplink Fast is enabled. For exam tips, Uplink Fast can't be used on the root bridge. It's meant only for switches that sit at the edge of the spanning tree topology. For example, the access switches. The next topic is Rapid PVST+. Rapid PVST+ is a Cisco protocol that enhances network stability by providing faster convergence time compared to traditional spanning tree protocol. Going back to PVST+, it would take around 50 seconds to go through the port states to communicate with the other switch. This is because traditional STP is based on timers. If you want to speed up the convergence process, you must lower the timers. But even then, you can't get lower than tens of seconds. To improve STP's performance, Cisco introduced enhancements to PVST+ like Uplink Fast and PortFast. These features help speed up network recovery, but they required extra setup. Here comes Rapid PVST+, that doesn't rely on timers to decide whether to put an interface in the forwarding state. How does Rapid PVST+ work? Rapid PVST+ is an enhancement of PVST+, and most of the terms and mechanics are still the same, with little differences. Let's take a look into the differences. In PVST+, only the root bridge generates and sends BPDUs. Other switches just forward those BPDUs they receive from the root. In Rapid PVST+, every switch actively generates its own BPDUs. They don't just forward the root BPDUs. Let's now understand the Rapid PVST+ port roles. Rapid PVST+ picks the switch with the lowest bridge priority value as the root bridge, and then assigns one of the following roles to each port. First is root port. This is the lowest cost path for the switch to reach the root bridge. Every switch except the root itself has one. Next is designated port. This port connects to the switch, offering the best path from that specific LAN segment to the root bridge. Then, there's the alternate port. It provides a backup path to the root bridge in case the current root port fails. Next is backup port. This port serves as a backup for a designated port. It's used when there are two links from the same switch to the same LAN segment or loop back. And the disable port. This port does not participate in the spanning tree. Only root and designated ports are part of the active topology. Alternate and backup ports are kept on standby and excluded from normal traffic flow. Next are the port states. Earlier, we discussed the spanning tree protocol port states: disabled, blocking, listening, learning, and forwarding. The Rapid PVST+ states is slightly different. It defines port states based on how the port handles incoming frames. Each port role can be in one of these three states. First is discarding. The port drops all incoming frames and doesn't learn MAC addresses. This state combines disabled, blocking, and listening states since none of them allowed forwarding. Next is learning. The port still drops incoming frames but starts learning MAC addresses. And last is forwarding. The port forwards incoming frames based on MAC addresses it has already learned and continues to learn. Rapid PVST Plus is designed for faster spanning tree convergence. Here's a breakdown of how Rapid PVST Plus achieves rapid convergence. First is point-to-point links. It leverages the assumption that links between switches are typically point-to-point or full duplex. This assumption allows for faster convergence because the protocol can rely on direct communication between switches rather than waiting for multiple devices to negotiate on a shared medium. Next is proposal agreement handshake. When a link failure occurs or a new device is added, the switch initiates a proposal message to its neighbors. The neighbor responds with an agreement message, and if the path is deemed optimal, both switches on the link will transition their respective ports to the forwarding state. This process of proposal and agreement allows for a rapid progression of the spanning tree from the root switch towards the leaves, minimizing the time it takes for the entire network to converge. Next is edge ports and rapid transition. The edge port connects to a single host and immediately goes to the forwarding state. If a BPDU is received on an edge port, it's treated like a regular port again. Rapid PVST Plus provides a significant improvement over traditional spanning tree protocol and allows for much faster convergence times, typically less than a second, compared to the 50 seconds or more that can occur with older STP implementations. For exam tips, traditional PVST Plus relies on timers to decide whether to put a port in the forwarding state. Rapid PVST Plus does not rely on timers but on proposal agreement negotiation. Rapid PVST Plus introduces new port roles, alternate and backup. The next topic is root guard. Root guard is a feature within Rapid PVST Plus that helps enforce the designated port role on specific interfaces, preventing unauthorized devices from becoming the root bridge and influencing the network topology. Why do we need root guard? Root guard prevents unwanted root bridge election. Imagine if someone disconnects their end device from the access switch and connects a rogue switch configured with a lower bridge ID. The rogue switch has a lower bridge ID and becomes the new root bridge because in spanning tree protocol, the switch with the lowest bridge ID always wins the election. Another case is if a network engineer accidentally connects a new access switch to the network that has some existing configuration and happens to have a lower BID than the rest of the switches, it becomes the root bridge. The root guard prevents rogue or misconfigured switches from disrupting the network by becoming the root bridge and potentially causing loops or suboptimal traffic paths. How does root guard work? Root guard is enabled on a per-port basis and enabled manually on each port where it's needed. It's disabled by default. When a switch receives a BPDU with a better bridge ID on a port with root guard enabled, that port is placed into special root inconsistent state. In this state, the port stops sending and receiving normal data traffic but continues to listen to BPDUs. This prevents the rogue switch from becoming the root bridge, and the network continues to function with the designated root bridge. Where do we use the root guard? We use root guard on ports where the root bridge should never appear. Typically on ports facing towards access or distribution layer switches, preventing unauthorized devices from becoming the root bridge. Let's now configure a root guard. We can enable it per interface with the following command in interface configuration mode. We can also check if any ports are in root inconsistent state using the following command. This will show if there's inconsistency with the root port. For exam tips, root guard is a feature that helps protect the spanning tree topology, and it works per port. It is recommended that root guard be used on the core and distribution layers on ports that face away from the primary and secondary root bridge. There's another spanning tree security feature called BPDU guard. BPDU guard is enabled on individual switch ports, specifically those configured with PortFast, to enhance network security by preventing unauthorized devices from becoming part of the spanning tree topology. It is generally configured on access ports that connect to end-user devices like laptops or workstations, rather than other switches. How does BPDU guard work? BPDU guard monitors for any BPDUs arriving at the port. When a switch port with BPDU guard configured receives a BPDU, the feature immediately disables the port by putting it into error-disabled state. The port then stays in an error-disabled state until someone manually re-enables it, or it recovers automatically after a timeout. Let's now configure BPDU guard. By default, BPDU guard is turned off on all switch ports. We can enable it globally or for specific switch ports. To enable BPDU guard globally, in global configuration mode, use the spanning tree PortFast BPDU guard default command. To enable BPDU guard on specific switch ports, enter the interface configuration mode and use the spanning tree BPDU guard enable command. We can also configure automatic recovery from error disable. If a port is shut down by BPDU guard, it won't come back up on its own. First, we enable the automatic recovery for the BPDU guard feature. We then specify the recovery interval. The following command sets the recovery interval to 300 seconds or 5 minutes. We can verify the current error disable recovery settings using the following command. It shows which causes are enabled for automatic recovery and the configured interval. For exam tips, enabling BPDU guard prevents users from accidentally or intentionally connecting rogue switches. Never enable BPDU guard on uplink ports that might receive BPDUs from the root bridge. If a switch has multiple uplinks, some of them may receive valid BPDUs even if they are currently blocking. Another spanning tree feature designed to protect the loop-free tree is the BPDU filter. BPDU filter is a feature that either prevents a switch port from sending or receiving BPDUs, or both. Why do we need BPDU filter? Edge port sends BPDU. This is part of the spanning tree protocol's normal behavior, which helps prevent loops by allowing switches to share topology information. However, sending spanning tree BPDUs to end devices is unnecessary because end devices do not participate in the STP process, which can also be a security vulnerability by exposing topology information to end devices. Another case is inter-organization connection. For example, two different organizations needing to interconnect their Layer 2 networks because of merger or shared services and applications. Each organization's network has a different STP domain with its own designated root bridge. If the organizations interconnect, the switches will exchange BPDUs and converge the two separate STP topologies into one with a common root bridge. The organization still wants to confine to its own network, and in these cases is where BPDU filter comes in. This is how BPDU filtering works. BPDU filtering can be configured to block either incoming or outgoing BPDU packets on a specific port. BPDU filtering can be enabled globally for all PortFast enabled ports or on a per interface basis. Let's break down the global and interface configuration. For BPDU filtering that's globally enabled, when the port comes up, it sends BPDUs out. If the port doesn't receive any BPDUs during that time, the BPDU filter starts dropping outbound BPDUs. At this point, the port remains in PortFast mode. If BPDUs ever arrive on that port, the port starts sending and receiving BPDUs normally. The port goes back to regular STP, ensuring no loops can form. For the interface configuration, BPDU filter drops all BPDUs in both directions on a port, effectively turning off STP for that interface. Once configured this way, the port ignores both incoming and outgoing BPDUs. Let's now configure BPDU filtering. We can configure BPDU filter globally or per interface. Let's start with the global configuration. This applies only to ports that are PortFast activated. To enable BPDU filter globally on a switch, we use the command spanning tree PortFast BPDU filter default. This command enables BPDU filter on PortFast enabled ports or edge ports. The following command shows how we verify if BPDU filter is configured globally on a switch. The output shows that BPDU filter is enabled. To configure BPDU filter on an interface, we configure it with the command spanning tree BPDU filter enable under the interface itself. To verify that BPDU filter is enabled on a port, we can use this command. The output does not say by default, which indicates that BPDU filter was enabled by the interface command, fully disabling the STP on that port. The zero counters confirm that all BPDUs are being discarded on this interface. The last topic in this section is LoopGuard. LoopGuard is a feature that enhances network stability by preventing forwarding loops, especially in scenarios where unidirectional links exist. What is a unidirectional link? In networking, sometimes we use fiber cables that are typically made of a pair of fiber strands, one strand for transmitting data, or TX, and the other for receiving, RX. If one of the two strands becomes damaged or fails, the link can become unidirectional. These problems can be hard to detect because the link may still appear up on one side, even though communication is broken in one direction. Why do we need a LoopGuard? Unidirectional link can cause a port to stop receiving BPDUs. The switch port then assumes a topology change and moves its port to a designated role and transitions it into the forwarding state that leads to a broadcast norm. The LoopGuard is designed to prevent layer 2 loops, particularly those caused by unidirectional link failures. How does a LoopGuard work? As long as BPDUs are being received, the port operates normally. But if BPDUs stop arriving, LoopGuard puts the port into a loop inconsistent state. This loop inconsistent state effectively blocks the port, preventing it from forwarding the traffic and thus avoiding a loop. When enabled on a port, it doesn't allow it to become a designated port when it suddenly stops receiving superior BPDUs. When the port starts receiving BPDUs again, it will automatically recover and resume normal STP operation. LoopGuard is particularly useful on non-designated ports, like the alternate and root ports, and is often recommended for ports connected to other switches, especially those using fiber optic cables where unidirectional links are more common. It should not be configured on ports with PortFast enabled, as it may interfere with port states. Let's configure LoopGuard. We can configure LoopGuard globally or per interface. To enable globally, use the spanning tree loop guard default command. To enable per interface, use the spanning tree guard loop command on a specific interface. Act as a central reference point where all path calculations in STP are made relative to it. How is the root bridge elected? The best path to the root bridge. Port states in rapid PVST+. Enables ports to go directly to the forwarding state. Use some access ports to avoid delay. Disables a PortFast port if it receives a BPDU. Protects against misconfigurations. Prevents a designated port from becoming a root port. Useful to protect the root bridge location. Prevents ports from transitioning to forwarding if BPDUs are unexpectedly missing. Protects against unidirectional link failures.